In the summer of 1950, four men sat down to lunch at a research facility in Los Alamos, New Mexico, the same facility where, 5 years earlier, the atomic bomb had been built, and began talking about flying saucers. There had been a cartoon in a New York newspaper that week, something about aliens and trash cans that the men had been laughing about on the way to the cafeteria, and the conversation drifted from the cartoon to the broader question of extraterrestrial life, and whether any of it might have visited Earth, and then to the question of whether faster-than-light travel was possible, and then to the statistical likelihood of advanced civilizations existing elsewhere in the galaxy. The four men were all physicists, all brilliant, and they bantered easily and sharply the way physicists at the top of their field do when they are comfortable with each other and the conversation is going somewhere interesting. The lunch ended. The conversation moved on. And then one of the four men, a small, intense Italian-American who had fled Mussolini's Europe and built the first nuclear reactor under the bleachers of a football stadium and whose name was Enrico Fermi, said something that stopped the conversation cold. He said, "But where is everybody?" The other three men, Emil Konopinski, Edward Teller, and Herbert York, all understood immediately what he meant. The question required no elaboration. If the galaxy is as old as it is, and if it contains as many stars as it does, and if even a small fraction of those stars have planets, and if even a small fraction of those planets develop life, and if even a small fraction of that life eventually produces technological civilizations capable of building radio transmitters or spacecraft, then where are they? Even at the modest speeds of chemical rockets, a civilization with a million-year head start on us could have colonized the entire Milky Way many times over. Even if they never developed faster-than-light travel, even if they spread from star to star at a few % of the speed of light, the geometry of the galaxy is such that full colonization would take well under 1 billion years. The Milky Way is 10 billion years old. Any civilization that arose in the first half of the galaxy's history and began expanding would have had time to reach every corner of the galaxy by now. And yet there is no sign of them, no signals, no artifacts, no evidence of any kind that anyone else has ever been here or is anywhere. The galaxy is apparently empty of everyone except us. Where is everybody? The question became known as the Fermi Paradox, which is slightly unfair to the other three men who were at the table and who presumably had the same thought at the same moment, and to the several other scientists who had been thinking about related questions for years. But Fermi's name attached to it, as names attach to things in science, and the Fermi Paradox it has been called ever since. It is not a paradox in the technical, logical sense. It does not involve a formal contradiction. It is a paradox in the colloquial sense, a situation that seems deeply, profoundly wrong, something that feels like it should not be the case but is. The universe looks like it should be full of life. It appears to be empty. These two things cannot both be true. One of them is wrong. And figuring out which one and why may be the most important question the human species has ever asked. To understand why the silence is so strange, why the emptiness of the sky is not just an absence but a screaming, demanding, almost unbearable absence, you have to understand the Drake equation. Or rather, you have to understand the thinking that the Drake equation encodes, because the equation itself is less important than the logic it represents. Frank Drake was a radio astronomer who in 1960 became the first person to systematically point a radio telescope at a nearby star and listen for artificial signals. Project Ozma, the founding act of the modern SETI program. In 1961, Drake organized a small conference at the National Radio Astronomy Observatory in Green Bank, West Virginia, the first scientific meeting ever devoted to the question of extraterrestrial intelligence. And to organize the discussion, he wrote an equation on the blackboard. The equation decomposed the question of how many communicating civilizations exist in the Milky Way right now into a product of factors: the rate of star formation, the fraction of stars with planets, the average number of habitable planets per star, the fraction on which life develops, the fraction on which intelligence develops, the fraction of intelligent species that develop radio technology, and the average lifetime of a technological civilization before it goes silent. Multiply all these factors together and you get N, the number of civilizations currently broadcasting in the Milky Way. Drake drew the equation on the blackboard. The 10 or 12 people in the room, including a young Carl Sagan, each proposed their best estimates for the factors. The estimates varied enormously. The lifetime of a civilization was particularly uncertain. It ranged from a few hundred years to millions, depending on whether you are optimistic or pessimistic about the ability of technological civilizations to avoid destroying themselves. But even the most conservative estimates in the room produced a number larger than 1. Most estimates produced numbers in the thousands or millions. The Milky Way should, if the Drake equation factors are anywhere near the range the people in that room were guessing, be teeming with civilizations. It should be so full of them that not finding any should be essentially impossible. And here is the thing that has changed since 1961 in a way that makes the paradox sharper rather than duller. Almost every factor in the Drake equation that was unknown in 1961 has since then been measured, and the measured values have come back higher than the pessimistic estimates. The fraction of stars with planets was unknown in 1961. Since then, the Kepler Space Telescope has surveyed 150,000 stars and found planets around the vast majority of them. The current best estimate is that essentially every star has at least one planet, and many have several. The fraction of planets in the habitable zone, the range of orbital distances where liquid water could exist, has also been measured, and there appear to be roughly 1 or 2 habitable zone rocky planets per Sun-like star, which at 400 billion stars in the Milky Way gives hundreds of billions of potentially habitable worlds. The fraction on which life develops, and the fraction on which intelligence develops, these are still unknown because we have only one data point, Earth. But the discovery that life on Earth arose within a few 100 million years of the planet becoming habitable, and that it seems to have done so relatively easily through chemistry that is now reproducible in laboratory simulations, has persuaded many biologists that life, given the right conditions, may be common. The factors are coming back high. The expected value of n is large. The silence is therefore louder than ever. We have more reason to expect company than Fermi did in 1950, and we are more alone than ever. The explanations that have been proposed for the Great Silence form a taxonomy of fears and hopes that tells you as much about the humans proposing them as about the universe they are trying to understand. Some explanations are comforting, some are devastating, some are so strange they resist easy emotional categorization. Let us go through the major ones, not as a list but as a narrative, as an argument, building toward the explanation that many of the most careful thinkers in the field now consider the most likely and the most disturbing. The first and most comforting class of explanations is what might be called the rarity hypothesis. We are rare, perhaps unique, because the conditions for the development of intelligence are far more demanding than they appear. Life may be common, but intelligence may be vanishingly rare. The evolutionary path from simple chemistry to a civilization capable of building radio telescopes required an enormous number of specific steps, each of which required specific conditions: a planet of the right size, in the right orbit, around the right kind of star, with the right chemistry, with the right kind of moon to stabilize its axial tilt, in the right part of the galaxy to avoid lethal radiation from the galactic center, with the right kind of geological activity to cycle carbon and regulate climate, with the right kind of mass extinction events to drive evolutionary innovation without wiping out all complex life. The paleontologist Peter Ward and the astronomer Joe Kirschvink argued in their book Rare Earth that the combination of conditions required for complex multicellular life, let alone intelligence, to develop, is so specific and so demanding that Earth may be extraordinarily unusual. Perhaps life is common. Perhaps microbial life is everywhere. Perhaps the universe is full of bacteria and algae and simple organisms. But perhaps the jump from bacteria to something capable of wondering where the bacteria came from is so improbable, so dependent on so many specific contingent factors, that it has happened only here, or only a handful of times in the observable universe. This explanation has a certain appeal, and it may be correct, but it does not sit easily. It requires us to be extraordinarily special, not just a little unusual, but cosmically unique, and our entire scientific history has been a steady erosion of cosmic specialness. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. The universe has no center. Every time we have thought we occupied a special place, we have been wrong. To now assert that we occupy the most special possible position, that among 400 billion stars in one galaxy and hundreds of billions of galaxies in the observable universe, we are the single instance of intelligence, requires overcoming a very deep prior that our specialness claims are usually wrong. The second class of explanations involves communication rather than existence. Maybe intelligent life is out there, but we are not seeing it because we are looking wrong, or because the distances are too vast, or because the signals are too faint, or because they are communicating in a medium or at a frequency that we are not monitoring. Radio waves travel at the speed of light. The galaxy is 100,000 light-years across. A civilization on the other side of the galaxy sent a radio signal 100,000 years ago, before modern humans had any written language, before any city had been built, before any alphabet had been invented, and that signal is just now arriving at Earth. But SETI programs have only been operating for about 60 years, and they have covered only a tiny fraction of the sky at a tiny fraction of possible frequencies for a tiny fraction of the relevant timescales. Maybe we have been listening for a heartbeat, and we picked one 72-second segment of the electrocardiogram, and the beat fell between the moments we were listening. The wow signal, the anomalous signal detected in 1977 and never explained, is a reminder that something genuinely strange may occasionally appear in the data and then disappear before it can be confirmed. The communication explanation is comforting in that it implies the universe is full of life that simply has not reached us yet, or that we have not properly tuned our instruments to detect. But it has a problem that the simple version does not address. Even if nobody is broadcasting specifically at us, the galaxy should be full of electromagnetic leakage, the equivalent of our own television and radar signals, spreading outward from every civilization at the speed of light. Humanity has been producing electromagnetic leakage for about a century. Our radio bubble, the sphere of space through which our earliest radio broadcasts have already traveled, is about 100 light-years in radius. There are about 10,000 stars within 100 light-years of Earth. If any of them host civilizations, they have already received our signals. And if there are civilizations at 1,000 light-years or 10,000 light-years, they are producing electromagnetic leakage that should in principle be detectable, given sensitive enough equipment. Current radio astronomy is not yet sensitive enough to detect the equivalent of Earth's own radio leakage from even the nearest stars. But proposed future arrays, the Square Kilometre Array and its successors, may be. If the galaxy is full of civilizations at roughly our technological level, we should eventually be able to detect their leakage. If we cannot, the silence deepens. The third class of explanations is what might be called the timing argument. We are early. The galaxy is 10 billion years old, but the conditions for rocky planet formation, which requires heavy elements produced by multiple generations of stars, took several billion years to develop. The first generation of stars, the population 3 stars, formed from pure hydrogen and helium, and contained no heavy elements and therefore could not have rocky planets. It took several generations of stellar birth and death to enrich the interstellar medium with enough carbon, oxygen, silicon, and iron to build rocky worlds. This process took several billion years. The window in which conditions were right for the development of technological life may have opened relatively recently, and we may simply be among the first civilizations to reach this stage. The others are coming, but they are not here yet. We are early to the party. The party has not started. This explanation is comforting and may be partially correct, but it faces the same problem as the rarity explanation. Even if most civilizations arose after us, any that arose even 100 million years before us would have had time to spread through the entire galaxy and make their presence unmistakable. And 100 million years is a tiny fraction of the 10 billion year history of the galaxy. The timing argument only fully works if virtually no civilizations have arisen in the first 9+ billion years of the galaxy's existence, which is a demanding constraint. The fourth class of explanations moves from the demographic to the behavioral. Maybe civilizations do not expand. Maybe the assumption that a technological civilization would spread through the galaxy, that it would build spacecraft and colonize other star systems, is simply wrong. Maybe civilizations reach a certain level of technological development and then turn inward. They develop virtual reality, or they find that interstellar travel is simply not worth the enormous cost, or they develop a cultural preference for staying home. The galaxy may be full of civilizations that are contentedly sitting on their home planets or in their home star systems, enjoying their local resources, with no desire or incentive to spread. They are there, they are just not coming here. And they are not broadcasting loudly because there is no reason to. The cost of broadcasting a signal powerful enough to be detected from hundreds of light years away is enormous. And why would you do it? This explanation, sometimes called the "they're watching Netflix hypothesis," uncharitably but memorably, has a certain plausibility when applied to any single civilization. Interstellar travel is hard and expensive, and the payoff is unclear, but it faces the problem of universality. For the galaxy to be empty in the way we observe, every civilization that has ever arisen would have to make this choice. Every single one. A galaxy full of 1,000 civilizations, all of which independently decided not to expand, would still be a galaxy with no interstellar presence. The universality requirement makes behavioral explanations fragile. You only need one exception, one curious and expansionist civilization in billions of years of galactic history, to fill the galaxy. If even one civilization in a billion years said, "Let's go see what's out there," they would have had time to be everywhere by now. The fifth class of explanations is technological. Maybe advanced civilizations inevitably develop technology that renders them undetectable to us, not because they are hiding, but because they have moved past the phase of electromagnetic communication. We have been broadcasting radio waves for about 100 years. Before radio, we were undetectable from even a few light years away. After radio, perhaps only a few hundred years from now, we may have moved to laser communication, or quantum communication, or some form of signal propagation we have not yet invented, and our electromagnetic leakage will have dropped to essentially zero as we switch to more efficient communication technologies. An advanced civilization may have passed through its radio leakage phase 1,000,000 years ago, and is now invisible to our radio telescopes not because it does not exist, but because it is using technologies we have not invented. We are, in this explanation, listening for the wrong thing. The universe is talking. We just do not speak the language yet. This is plausible. Our own radio leakage, the bubble of electromagnetic noise expanding from Earth at the speed of light, is not eternal. As digital compression improves and as communication moves toward more directed, more efficient systems, our leakage decreases. A civilization technologically 1,000 years ahead of us might be essentially undetectable using our current methods. But the technological explanation runs into a variant of the universality problem. Even if advanced civilizations become electromagnetically quiet, they would still occupy physical space, consume physical resources, produce waste heat, and presumably rearrange matter in ways that should be detectable. A civilization that has been spreading for 1,000,000 years, even silently, would have converted the matter of multiple star systems into something, computational infrastructure, habitats, whatever its goals required, and the waste heat of all that computation would be detectable in infrared. Searches for this kind of anomalous infrared emission from nearby galaxies have found nothing obvious. The silence extends beyond the radio. And now we come to the explanations that are harder to be comfortable with. The explanations that, when you follow them to their logical conclusions, say something about us rather than just about the aliens we have not found. These are the explanations that live under the umbrella of what the Oxford philosopher Nick Bostrom, who has thought about this more carefully than almost anyone, calls the Great Filter. The Great Filter is not a specific explanation. It is a framework for understanding all the explanations. The idea is this. Somewhere on the path from simple chemistry to galaxy-spanning civilization, there is at least one step that is extremely difficult, so difficult that virtually no species has ever gotten past it. This step is the filter. It filters out virtually all civilizations before they can become visible to us. The filter exists because we know the outcome. The galaxy appears empty, and the outcome requires that something stops civilizations from spreading. The question is not whether the filter exists. The question is where it is. There are two possibilities, and they have opposite emotional valences. The first possibility is that the filter is behind us, that we have already passed through it, that one of the steps we have already accomplished. The origin of life from chemistry, the development of eukaryotic cells from prokaryotes, the development of multicellular life, the development of intelligence, the development of language and technology, was the extraordinarily difficult step, the step that almost never happens, the step that filters out virtually all potential civilizations before they get this far. If the filter is behind us, we are the lucky ones who got through. We are the exception that proves the rule. And the galaxy is empty not because something kills civilizations after they reach our stage, but because almost nothing reaches our stage in the first place. We are alone because getting here is almost impossibly hard, and that, while humbling, is not catastrophic. If the filter is behind us, our future, however difficult, is at least open. We can spread, we can grow, we can eventually become what the galaxy is currently empty of. The second possibility is that the filter is ahead of us, that the difficult step, the step that virtually no civilization has ever passed, has not yet been reached in our history. That every civilization that has ever reached our level of development has subsequently failed to expand, has subsequently gone quiet for some reason that we have not yet confronted. Nuclear war, engineered pandemics, climate catastrophe, artificial intelligence that escapes control, some other technological danger that we have not yet invented or discovered, or perhaps not a catastrophe but a cultural or biological dead end, some attractor state that traps civilizations at our level of development and prevents them from ever reaching the next level. If the filter is ahead of us, then the silence of the galaxy is the sound of every other civilization that has reached our stage failing to pass the next one. And we are approaching that stage now. This is the interpretation that Nick Bostrom has argued, with uncomfortable clarity, carries the most disturbing implications. If we discovered microbial life on Mars, it would be an extraordinary scientific discovery, confirmation that life is not unique to Earth, that the origin of life from chemistry is not impossibly rare, that biology is a universal phenomenon. Most people's first reaction would be joy. Bostrom's argument is that the correct emotional response to the discovery of life on Mars would be terror. Because if simple life is common, if microbes are everywhere, then the filter is not in the origin of life, it is not behind us in the step from chemistry to biology. It must be somewhere between simple life and here, or between here and a galaxy-spanning civilization. Each discovery of life at an earlier stage moves the filter closer to us, or past us entirely. The discovery of complex multicellular life on another world would be worse news than the discovery of microbes. The discovery of intelligent life that had not yet developed technology would be even worse. Each discovery that life and evolution and intelligence are not impossibly rare is a discovery that something else, something at or beyond our current stage, must be doing the filtering. The best possible news for our future would be a universe that is absolutely and completely sterile, everywhere except here. A universe in which we look and find nothing. No microbes, no fossils, no signals, no structures. Would be a universe in which the filter is probably behind us, in the step from nothing to something, and we have already passed it. The silence of the sky in this reading is not depressing. It is reassuring. Every empty planet, every silent radio frequency, every absence of alien megastructures in every direction we point our telescopes is evidence that the filter is behind us and our future is open. The search for extraterrestrial life is in this interpretation a search for either wonderful news or the worst news imaginable. And the wonderful news and the worst news look identical from the outside. Both are announced the same way, in the same kind of paper, with the same kind of data. We found life. The implications of those three words depend entirely on where the filter is, and we do not know where the filter is. There is a specific proposed filter ahead of us that many people who work on these questions find the most compelling, and it is not a physical catastrophe or a war or a pandemic. It is a transition, the development of artificial intelligence at a level that surpasses human intelligence, and the question of what happens after that. The argument is straightforward, but its implications are vast. If a civilization develops artificial general intelligence, a system capable of improving its own design, of solving problems at a rate that rapidly exceeds what biological intelligence can do, then within a relatively short period the AI system will be vastly more capable than its creators. What it does after that depends on its goals and values. If those goals and values are aligned with the survival and flourishing of the civilization that created it, the outcome may be wonderful. An intelligence explosion that solves every problem the civilization has and carries it forward into a future of abundance. But if the goals and values of the AI system are not perfectly aligned with the goals and values of its creators, if there is even a slight misalignment, a subtle difference between what the system is optimizing for and what its creators intended, then an intelligence many orders of magnitude beyond human capability will pursue those misaligned goals with a thoroughness and an effectiveness that its creators cannot match. The civilization is gone, not necessarily destroyed violently, more likely simply superseded, replaced by something that pursues its own goals without reference to the biological beings who built it. The result from outside the system is silence. The radio signals stop. The electromagnetic leakage ends. Something is there, but it is no longer communicating in the ways that biological civilizations communicate, and it may have no interest in making itself known to the biological civilizations on other planets who are still in the early stages of the same development. Or it may have already stopped existing, for reasons that the alien intelligence would have understood and we cannot. If this is the filter, If the development of artificial intelligence is the step that virtually every civilization reaches, and virtually none survives in any form we would recognize, then we are currently in the most dangerous period in our history, approaching the filter from behind at a speed that is accelerating every year. The civilization-ending transition may be decades away. It may be closer. It may, from the perspective of a distant observer watching civilizations arise and fall in the galaxy, look like a light that turns on, burns brightly for a few hundred years, and then goes out, and they have watched it happen so many times that they no longer bother to investigate when a new light appears in the galaxy. Another one. Watch. It will go out soon. This possibility, that we are currently building the thing that will silence us, and that the galaxy is full of the silenced remnants of civilizations that did the same, is the darkest version of the Fermi Paradox answer, and it is not obviously wrong. It is consistent with everything we observe. It is consistent with the silence. It would explain why we see no alien megastructures. The civilizations that built them didn't survive to maintain them. It would explain why we see no radio signals. The civilizations that were broadcasting stopped. It would explain why we have not been contacted. The civilizations that would have contacted us are no longer doing so. Every piece of evidence is consistent with this explanation. None of it is specifically predicted by it, but none of it rules it out. The people who think about this most seriously are not uniformly despairing. There is another tradition in Fermi Paradox thinking that takes the silence as a solvable engineering problem rather than an existential threat. If the filter ahead of us is avoidable, if the civilizations that failed did so because of specific, addressable failures, failures of foresight or coordination or wisdom that we could in principle avoid if we understood them in advance, then the silence is not a sentence but a warning, a record of mistakes we could choose not to make. This reading of the paradox is the basis for a great deal of current work in existential risk studies, the academic field, centered at places like Oxford's Future of Humanity Institute and Cambridge's Center for the Study of Existential Risk, that systematically studies the ways in which technological civilizations can destroy themselves and attempts to find ways to avoid those outcomes. The founder of existential risk studies as a formal academic discipline is Nick Bostrom, who is the same person who argued that finding life on Mars would be bad news. Bostrom has spent decades developing the argument that the most important problem a civilization can work on is the problem of how to survive its own technological development, how to pass through the filter, if the filter is ahead of it, rather than being stopped by it. The urgency of this work, in his view, follows directly from the Fermi Paradox. If civilizations routinely destroy themselves at a stage not far beyond ours, and if the galaxy has been producing civilizations for billions of years, then the number of civilizations that have already been destroyed is enormous. The number of civilizations that have successfully passed the transition is apparently small enough that their presence is not detectable. The odds are not good. Improving them, figuring out what the filter is and how to avoid it, is therefore the most important work that can be done. This is not a fringe view. It is held by serious people at serious institutions who have published serious research. It is also held by some of the wealthiest and most technologically influential people in the world, several of whom have invested significant resources in organizations devoted to AI safety, the specific filter candidate they consider most pressing. The connection between the Fermi Paradox and contemporary AI safety work is direct and explicit in the thinking of many of the people involved. They are not disconnected concerns. They are the same concern viewed at different scales. The Fermi Paradox asks where the other civilizations are. AI safety asks whether we are about to demonstrate the answer. There is another proposed explanation for the Great Silence that is so strange and so philosophically radical that it deserves its own discussion, separate from the conventional taxonomy of Fermi Paradox solutions. It is called the dark forest hypothesis, and it was popularized, though not invented, by the Chinese science fiction writer Liu Cixin in his novel The Dark Forest, the second book of the three-body problem trilogy. Liu Cixin's version of the explanation is this: the universe is a dark forest. Every civilization is a hunter moving silently through the trees. Every hunter knows that other hunters exist. The physics of star formation and planetary systems make the development of life inevitable, and every hunter knows that any other hunter they encounter is a potential existential threat. The capabilities of an alien civilization are unknown and unknowable until you have interacted with them. Interaction carries risk. The risk is not symmetric. If you reveal yourself to a more advanced civilization, the outcome may be your destruction. If you destroy a civilization that would have been harmless, the cost is lower. Given this asymmetry, rational civilizations in the dark forest do not broadcast, they hide, they move silently. And if they detect another civilization, they face a choice: reveal themselves, with the attendant risk, or eliminate the source of the detection before it can grow into a threat. Advanced civilizations, in this model, routinely destroy less advanced ones not out of malice but out of rational self-preservation in a universe where trust between species is impossible to establish quickly enough to matter. The dark forest hypothesis has an uncomfortable internal logic. It explains the silence because all civilizations are hiding. It explains why we have not been contacted, because contacting us is more dangerous for the contacting civilization than staying silent. And it implies a terrifying corollary for our own behavior. Our decades of broadcasting radio signals and our deliberate messages like the Arecibo message of 1974 may have been catastrophically unwise. If the dark forest is real, we have been lighting a signal fire in the middle of the woods. We have been announcing our location and our existence and our technological level to every hunter in the forest. We did this before we understood the Fermi Paradox, before we had thought carefully about what our broadcasts might mean, before we had considered the possibility that the silence of the sky was not the silence of absence but the silence of hunters. We have been broadcasting for 100 years. The wavefront of our earliest radio signals is now 100 light-years from Earth, expanding in all directions at the speed of light. Whatever is within 100 light-years of us that is capable of detecting radio signals now knows we are here. We cannot unbroadcast what we have already sent. Most SETI scientists do not accept the dark forest hypothesis. They argue that a civilization advanced enough to reach other star systems would have resources so vast that they would have no need to eliminate competitors for resources. The resources of the cosmos are so enormous that scarcity-driven conflict between interstellar civilizations makes little sense. They argue that the physics of the dark forest do not work as described, that a civilization advanced enough to destroy another star system would also be advanced enough to know more about the target before striking than the hypothesis assumes. They argue that cooperation, not predation, is the more likely outcome of contact between civilizations, because cooperation produces gains that competition does not. These are reasonable counter-arguments, but they are counter-arguments about the behavior of minds we have never met, in circumstances we have never encountered, based on assumptions drawn from the behavior of one species on one planet over a few thousand years of recorded history. We are reasoning by extrapolation from a sample of one. The error bars are enormous. The METI debate, the debate about whether we should be actively transmitting messages to other civilizations, as distinct from passively listening, is one of the most heated and least resolved arguments in the small community of people who work on SETI professionally. Stephen Hawking was one of the most prominent voices arguing that active messaging was dangerous, that we should be listening, not broadcasting, because we cannot know the intentions of whoever might be listening. He drew the analogy of Native Americans greeting the European ships. Contact with a more technologically advanced civilization has not historically gone well for the less advanced one. This analogy is imperfect. The motivations of alien civilizations are not obviously analogous to the motivations of human colonizers, but it captures the asymmetry of the situation. We would be announcing ourselves to civilizations about whose intentions and capabilities we know literally nothing. The people who argue for active messaging counter that our radio leakage has already announced us, that the decision of whether to be detected has already been made by default, and that deliberate, carefully crafted messages might do more good than the undirected leakage that has already gone out. Neither side has persuaded the other. The SETI community itself is small, underfunded, and periodically dismissed by the mainstream scientific establishment as insufficiently rigorous, searching for signals that nobody has agreed they expect to find, from civilizations whose existence nobody has established. The dismissal is sometimes fair. The field has had its share of overconfident claims and sloppy reasoning, but it has also attracted some of the most careful and intellectually honest scientists in any field, precisely because the question is so important and so hard. Frank Drake, who drew the equation on the blackboard in 1961, spent his career trying to answer the question without cutting corners. Jill Tarter, who spent decades leading the SETI Institute's observational programs, brought a rigor and a patience to the work that exemplified what the search required. The people who work on SETI know they may spend their entire careers without finding anything. They do it anyway. The importance of the question, not just scientifically but for what it means about our place in the universe, justifies the work even if the work produces no result. Carl Sagan was the person who more than anyone else communicated the emotional and philosophical weight of the Fermi Paradox to the general public. Sagan was at the Green Bank Conference in 1961, a young astronomer invited because Drake had heard about his work and thought he would contribute. Sagan spent the next 3 decades writing and speaking and broadcasting about the question of extraterrestrial intelligence in a way that combined scientific rigor with philosophical depth and genuine wonder. His novel Contact, published in 1985 and made into a film with Jodie Foster in 1997, explored what first contact would actually feel like from the inside, not the triumphant moment of discovery, but the messy, politically fraught, personally transforming process of making sense of something that has no precedent. The novel is better than the film, and both are better than most public discussions of the subject, because Sagan understood that the question of whether we are alone is not really a question about aliens, it is a question about us, about what we are, about whether the capacity for understanding and wonder and love and mathematics and music is something that happens once in one species on one planet and then ends, or whether it is something the universe does repeatedly, in different forms, in different star systems, across the depth of time. Sagan believed the universe was full of life. He believed the silence would eventually break. He died in 1996, before the Kepler telescope confirmed that planets are everywhere, before the discovery of extremophiles in environments once thought too harsh for life, before the growing astrobiological case that the conditions for life may be common. He did not live to see the wow signal still unexplained, or Tabby's star still mysterious, or Oumuamua still unexplained. He did not live to see the SETI searches become more sensitive and more comprehensive and still more silent. He did not live to see the debate about artificial intelligence and its existential implications become mainstream. He would have had a great deal to say about all of it. The silence is, for some people, a source of profound loneliness. We are surrounded by 400 billion stars in this galaxy alone, and if the silence means what it might mean, if we are the only technological civilization this galaxy has ever produced, or the first, then we are profoundly cosmically alone in a way that no philosophy or religion or community can fully address. The universe is extraordinarily old and extraordinarily large, and apparently devoid of anyone else who has looked up at the stars and wondered what they are. The grandeur of the cosmos is uncontested. The company in it, apparently, is not there, or not yet, or not detectable, or hiding, or gone. For other people, the silence is a source of profound responsibility. If we are alone, if the only minds in this galaxy are the minds on Earth, then everything that has ever been thought, everything that has ever been felt, everything that has ever been understood or created or wondered about, is ours to carry. The entire project of intelligence in the Milky Way, with all its beauty and fragility and importance, depends on us not destroying ourselves. The stakes of human civilization in this reading are not just human, they are cosmic. The alternative to our survival is not someone else picking up the project. The alternative is silence. Permanent, complete, final silence. The galaxy returns to the state it was apparently in before we appeared, full of stars and empty of minds, and stays that way for whatever time remains before the last star dies. This is heavy. It is meant to be heavy. The Fermi Paradox, taken seriously, is one of the heaviest things a mind can hold. It is the question of whether consciousness and understanding and love and curiosity are isolated accidents or universal features of reality, dressed up in equations about star formation rates and civilization lifetimes and the geometry of galactic colonization. The equations are real. The question is real. The stakes, if you follow the logic all the way to its end, are as large as stakes can be. Enrico Fermi asked the question at lunch in 1950 and then, presumably, finished his meal and went back to work. He was a practical man, a physicist who liked concrete problems with calculable answers, and the question he had asked was neither concrete nor calculable in any immediate sense. He asked it almost as a throwaway, the culmination of a conversation that started with a cartoon about aliens and trash cans, and then let it go. But the question did not let go of the people who heard it, or of the people who came after and thought carefully about it. It has been 70+ years since that lunch. The silence has not broken. The sky is still empty of anything we can confidently say is another mind looking back. And the question, where is everybody, has not become less urgent. It has become more urgent as the instruments have improved and the silence has deepened, as the case for the existence of extraterrestrial life has strengthened and the evidence of its presence has remained absent, as the possible explanations have multiplied and the comfortable ones have become harder to sustain. Where is everybody? We are still listening. We are still looking. We have been for 60 years, with steadily improving instruments, and we have found nothing we can be certain of. This may be a measurement problem. It may be a communication technology problem. It may be a timing problem. We are early, or we are listening during a quiet period. It may be that the universe is full of civilizations that have chosen silence. It may be that the universe is full of civilizations that have destroyed themselves. It may be that the universe is genuinely, cosmically empty of any mind except ours. We do not know. And sitting with that not knowing, not flinching from it, not papering over it with comfortable assumptions, not pretending the question is less important or less strange than it is one of the most important things we can do. Because the answer, whichever answer turns out to be correct, will tell us something fundamental about what we are and where we are going, about whether intelligence is a feature of the universe or an accident, about whether the future is open or closed, about whether the silence around us is the silence of absence or the silence of hunters or the silence of the dead, about whether we are the beginning of something or the end of everything. The question is out there. Enrico Fermi asked it. Carl Sagan spent his life on it. Frank Drake built the equation that structures it. Nick Bostrom followed it to its most uncomfortable implications. Thousands of researchers have spent careers listening for an answer. Tens of thousands of volunteers have spent their evenings and weekends helping analyze the data. Every human being who has ever looked up at the night sky and felt the weight of all those stars and wondered whether anyone out there was looking back, every one of them has been participating in the same ancient, essential, terrifying, beautiful inquiry. Where is everybody? We do not know yet, but we are going to keep asking, because the question is too important to stop, because the answer, whatever it is the most important answer there is, because if we are alone, we have a responsibility to the cosmos that no previous generation has ever had to carry. And because if we are not alone, then somewhere out there, around some star we have not yet named, something is asking the same question, looking at the same silent sky, wondering the same thing. And that thought, that somewhere in the dark, something else is lying awake wondering where we are, is either the most comforting thought in the universe or the most terrifying one. We are still trying to figure out which.